Hello, oceanographers. This is part 2 of our geologic features notes. Okay, so earlier we were talking about general tectonic activity, seafloor spreading, subduction zones. But we want to get now thinking about, well, how do these different types of activities create specific types of ocean floor features like islands and seamounts and trenches? And that has to do with the plate boundary types and the tectonic activity associated with those plate boundary types. So there are three basic boundary types. One like this is a divergent plate boundary where the plates are coming apart. The divergent plate boundary is where we have our mid-ocean ridge. And the second type is a convergent plate boundary. And a convergent plate boundary is when one plate goes underneath another plate. This happens at a subduction zone, and a feature that we'll see from there is a trench. And the third type is a transform plate boundary, where plates are sliding past each other. In fact, if we zip back and look at our plates here, here's an example of a divergent plate boundary. Plates are coming apart. Here's an example of a convergent plate boundary where the Pacific plate is pushing into the North American plate. And here's a good example of a transform plate boundary where the plates are sliding back sort of side and forth with each other there. Okay, in terms of what kind of features do these plate boundaries create, we look here at a divergent plate boundary. Like I said before, we have the mid-ocean ridge, and it sort of has this little rift zone right where the plates are coming apart. But as the magma comes up and these underwater volcanoes are made, it makes this mid-ocean ridge. This image right here is very similar to the Atlantic Ocean. We have our mid-ocean ridge in the middle, some abyssal plains, and then continents on either side. At a convergent plate boundary, two situations can occur. We can have a situation where ocean crust is going underneath a continental crust. In that case, we do get a trench, and as we've sort of seen before, as some of the crust melts, it can come up and create volcanoes. This is similar to the Andes Mountains in South America, and as I mentioned earlier, some of the Cascade Mountains up in northwestern United States and western Canada. You can also have a situation where you have an ocean plate going under another ocean plate. This is an example right here. Ocean plates going underneath another ocean plate, and again, the crust can sort of melt, be recycled, comes back up as volcanoes, and creates these island arcs. This is similar, I said earlier, as like Japan. There is a trench, but then near that trench are this island arc system. And again, there are lots of earthquakes associated with there. So if you live near a convergent plate boundary in a subduction zone, the chances of you being near an earthquake or experiencing an earthquake and being near a volcano are pretty big. We can put an image up here of transform plate boundaries. They don't create major geologic features, but they could cause earthquakes, and that can create tsunamis. All right, quick little side here, just sort of a quick note on basically the rock cycle. One thing that's important to understand is that all the rocks that are on land will eventually end up in the ocean, and this is due to weathering and erosion. Weathering is from rain, sleet, snow. Weathering breaks down the rocks on the continent, and then erosion is when that rocks wash down in streams, rivers, and into the ocean. But then those rocks can be deposited as sediment and create new rocks, or that rock could be pushed into the mantle and form again as a volcano and create new rocks that way. So the rocks are constantly being recycled. They're being broken down through weathering and erosion, and they're being formed through sedimentation, accretion, and volcanism. This is a little diagram from your book that kind of can show both of that. In fact, this shows how India, the continent of India, 45 million years ago was actually apart from Asia, but it collided into Asia. In fact, right now there's a huge collision. India is still crashing into Asia, and if you think of it like two cars running into each other, that one car that hits, it all crumples up in the front. In the hood of the car, it's kind of like India here. It's crumpled up and created the Himalaya mountains. So this process kind of sort of pushes the mountains up and can also create some volcanic activity. This makes new rocks, and as the rocks are pushed up, that can create bigger mountains. So rocks are being made in that case. In fact, rocks again are being made here at the mid-ocean ridge. But then those rocks are eroded, washed down through the river valleys into the ocean and created as sediment. That sediment ends up in the crust, but then that crust can be pushed underneath and recycled into volcanic rocks again. So it's important to keep thinking about how rocks are continuously recycled through the rocks through the rock cycle. All right, so let's put all this together. Oops, jumped ahead a little bit there. One other thing to think about is that the edges of continents and the edges of plates aren't always the same. And you can have situations, if we look back at our map of the plates here, situations where the edge of a continent is not near the edge of the plate. Like in this situation, the North American plate, we're actually near the edge of the continent, near the edge of the ocean, but in the middle of the plate. There's other situations like here on the West Coast where we are both at the edge of the continent and at the edge of the plate. There's some specific terms for those types of edges, or we call them margins. Where the edges of a continent are also the edge of the plate, it's known as an active continental margin. It's active because there might be a subduction zone going on, or they're transform plate boundary, and because there's that coming together or sliding past each other, there's lots of volcanoes and earthquakes. It's very active. It's called an active continental margin. If you're at the edge of a continent that's not near a plate boundary, but it's in the middle of the plate, it's called a passive continental margin. And it's passive because there's not a lot going on. We live at a passive continental margin. Lucky us. That's why we don't have a lot of earthquakes or volcanoes. This is an image of a passive continental margin. And some key features just to note in here that occur on the ocean floor at passive continental margin are the continental shelf, then the continental slope, the continental rise, and then the abyssal plain. So if we imagine, if we were in a car, we drove to New Jersey, and this car was sort of like a submarine car. You could drive it into the ocean, and it would stay on the floor of the ocean and keep driving along. We'd drive across New Jersey, we'd go right over the beach, and we'd head across the continental shelf. It really wouldn't get that deep. We'd probably drive for almost 100 miles, maybe in 100, 200 feet of water, but it'd be pretty darn flat, almost as flat as southern New Jersey. We drive along the continental shelf to eventually we reach the edge of the shelf. And this is kind of where the edge of the continent really sort of is. We then fall down the continental slope. We drive down that. We probably go a little bit faster as we go down the continental slope. After that, we reach the continental rise. And the rise is kind of where a lot of the sediment that's washed up and over the continental shelf is deposited. And eventually, once we reach kind of the far edge of the continent, then we'll reach the abyssal plain, which is a very, very flat underwater plain in the bottom of the ocean. The continental shelf, the slope, and the rise are all formed from the weathering erosion of sediment that had been up on the continent, washed in there, and then washed down into this area. All right? Now, putting it all together, this is a very important sort of diagram. This shows all the different features that are on the bottom of the ocean basin. And in fact, please keep note, these features are important for the bathymetry lab that you'll be doing soon. The bathymetry is sort of the mapping of the ocean floor, and you'll be doing that in our in-class activity. So again, at a passive continental margin, you have the continental shelf, slope, and rise. Here we are driving down. Then there's the abyssal plain, and most of the ocean floor is abyssal plain. Most of the ocean is about 4 kilometers deep. Then you have the mid-ocean ridge, as we talked about, at a divergent plate boundary. There are features called seamounts, which we'll talk about a little bit later on. And then if you're at a active continental margin, this could be where one plate is going underneath another plate. You'll have a trench. You'll still have a slope and a shelf, but you probably have a lot of earthquakes, and probably down here, magma can come up, and you could probably have volcanoes over here. So the shelf, slope, and rise, the abyssal plain, the mid-ocean ridge with its little rift valley in there, seamounts along the abyssal plain, and an ocean trench are the key features you'll need to know for your bathymetry activity. Okay? All right. Now I want to talk about some other just unique features at some of these ocean floor features. That includes something called turbidity currents. Turbidity currents occur when sediments that's washed through rivers kind of washed onto the continental shelf, and they sort of slip down these underwater canyons. In fact, these canyons are pretty neat. Some of the canyons are gigantic. In fact, there's a canyon off of Monterey Bay in California. That canyon is deeper than the Grand Canyon. What happens is sediment can be washed down those canyons and create what's called turbidity currents. And as you can see, the sediment flows down and then is deposited on the continental rise. So turbidity currents can occur at the continental shelf and slope and continental rise. Another unique feature that occurs over the abyssal plain are seamounts and volcanic islands, and these form from what we like to call hot spots. Now, if you look here, you can see that Hawaii is a volcano, is formed from a volcano, but Hawaii is actually in the middle of the Pacific Plate. So how did Hawaii get there? It's formed by something that geologists call a hot spot, and scientists aren't 100% sure what causes hot spots, but it's a place where the magma kind of comes up and bursts through, punctures through the middle of the plate. And as it punctures through, the magma comes up, cools as lava, and can create, either if it's still underwater, a seamount, or if it builds and grows and comes above the surface of the ocean, it becomes a volcanic island. In this case, what's unique is that as this hotspot is making underwater mountains or islands that come up above, the plate is moving over it. And so what happens is, over millions of years, the hotspot might make an island, but then an island, like a conveyor belt, is sort of moved away because the plate's moving. And then the hotspot will make another volcanic island, and then the plate would move it along. And so in time, from the one hotspot, all of these different islands are made. And in fact, the Hawaiian chain of islands are all made from the same hotspot. In a couple million years, probably 1 or 2 million years, the Hawaiian island, where the active volcano is, will move because the plate's moving northwest, and the new Hawaiian island will be made because the hotspot will make a new island chain. You can see here, the actual Hawaiian island chain goes way out there, past Midway Island, all the way up almost to the end of the Aleutian Islands near Alaska. And some other unique features of the mid-ocean ridge, 2 are pillow lavas and hydrothermal vents. Remember that mid-ocean ridge is where the plates are coming apart, magma's coming up, and as that magma oozes through the surface, it touches the ocean water at the bottom. It doesn't erupt necessarily violently, it kind of oozes out and then cools quickly and creates these sort of pillow rocks that are sort of shaped like pillows. And as more magma comes up, it shapes these rocks that are formed sort of like pillows. That's why it's called pillow lavas. And in fact, people can find pillow lavas that have made it to the surface above the ocean, and they do look sort of like pillows. Another unique feature are hydrothermal vents. These also occur at the mid-ocean ridge. Hydrothermal basically means sort of hot thermal hydro water vents. And where ocean water is seeping into the crust, it heats up where the magma is coming up, and then super hot water comes up. That super hot water brings with it lots of minerals, and those minerals are then sort of deposited along the edge of the mid-ocean ridge. These minerals are very valuable, and in fact right now there's lots of energy efforts by mining companies to see if we can collect these unique minerals that are deposited near the mid-ocean ridge. If you can imagine, though, it's in the middle of the ocean, at the bottom of the ocean, kind of a hard place to get minerals, but if it's valuable enough, people are going to try to do it. The other unique thing about this area is that this energy from this hot water coming up can create its own ecosystem. We'll talk a little bit more of that when we get to the ecology, underwater ecology, but scientists only have recently discovered there's tons of life, again, in the middle of the ocean, at the bottom of the ocean, where these hydrothermal vents occur. There are these long tube worms and crabs, and there's a whole ecosystem whose energy supply does not come from the sun, but actually comes from the energy of the interior of the Earth. Lastly, the big idea to wrap up these notes is that to think that the changes of the ocean floor could either occur very quickly in sort of catastrophic events like earthquakes or volcanic eruptions, or they can occur very slowly over millions of years like seafloor spreading. There's actually, if you can click here for a video, you can see the birth of an island as a volcano erupts and creates a new island right out of the ocean. That's a very catastrophic, quick kind of change. And again, if you think of the plates splitting apart and the ocean basin of the Atlantic moving further apart, that's a very slow example of change. But all in all, the features of the ocean's bottom are not staying the same. They change over time. They're constantly being formed and destroyed because of the moving of the plates. All right, this is the end of your first set of notes. Please feel free to email me with questions if you have them. Take care. Bye-bye.